All right, g'day everyone. Thanks for the opportunity to speak today. There's a fair bit to cover this afternoon, so I might just move straight into it. Important information and disclaimer. Standard information disclaimer. This is all just says I'm a reasonably competent person, but take everything I say with a bit of a grain of salt. Please understand that these are exploration results only, and any forward-looking statements are in general terms only. So where are we, and what has Sandfire been doing? We hold approximately 846 square kilometres of tenure through the Macquarie Arc, from Wellington North, just to our view here, from Wellington North up towards Boda, down south to our Temora project, which will be the area of discussion today. We have identified at least 5 separate alkalic porphyry systems across our Temora tenure, which also includes the Gyuris high sulphidation epithermal in the south that still retains 8 million tonnes of inferred resource at 1.53 grams per tonne. But the focus of today will be Fields, the Fields intermediate to low sulphidation epithermal system, which was discovered in 2019, really 2020, and occurs south of our porphyry province, but north of Gyuris in what we call our epithermal district. But why do we have an epithermal district in an Ordovician arc? Preservation is key. Considering that epithermals generally occur within the top 2 kilometres of crust, preservation from erosion is key in such an ancient arc. What has aided preservation? Well, taking a look at the TMI image that you can see on the right, there are 2 main features, 2 main striking features about it. There's, first of all, is a major arc normal transform fault just near Fields, and to the south is the Gear shear, which is to the south of Gyuris. To the north of the Fields prospect, the Rainhill batholith has largely been unroofed, while to the south of Gyuris, covered by Siluro-Devonian sediments, exceeds 200 metres in thickness, and basically it's all indicating there is sequential south block down movement, effectively a Goldilocks zone. So let's have a closer look at our geology. So on the left here, we have our geological interpretation, followed by TMI and Bouguer gravity on the right. In the north, the Rainhill in pink, as defined by the gravity, and to the south, brown, boring sediments. So our first order faults create effectively a wedge of thickened, tightly folded basaltic to andesitic lavas and volcanic clastics. It's arc crust. This sequence actually thickens to the south, the further south you go, between the transform fault in the north and the Gear shear in the south. We have second order shearing during transpression. They almost look like Rydell shears, basically semi-parallel to the strike of the arc. And our third order faults form an array of sinistral strike slip faults to the west, and over in the northeast, an imbricate set of thrust sheets, which formed during compression and presumably arc closure. The thickening of the crust, particularly to the south, and the sequential block down movement creates basically a zone of preservation, ideal for epithermal deposits, and vertical block rotation, particularly towards the south, has aided the preservation of high sulphidation epithermal deposits, which typically form very high in the crust. So, local geology. What controls the mineralisation? So this is our best interpretation of the broad sequence of events related to the Fields epithermal system. Our latest phase of intrusion, the earliest phase of intrusion, is a direct equivalent of the Rainhill monzonite. It's the one on the left, the coarse grain equigranular. It's sometime after its cooling and crystallisation, it underwent the transform faulting, and along that transform fault was emplaced a number of later intrusions. So we basically stepped down through our textures from medium crystalline, equicrystalline monzonite down to our fine grained porphyritic intrusions. Sometime during the end of that period was our mineralisation event, and as we can see in that picture on the right of one of our breccia veins, there's quite a bit of post-mineral modification. So, as we can see from this cross-section, it's a pretty complicated mess of intrusions and faulting. The known extent of fields that they've identified, we can see in red over here, occurs over a 650 metre strike length between two thrust sheets, and it's anticipated to continue into the footwall underneath the eastern thrust sheet. The long section along that strike is no less of a mess and gives you an insight into one of our biggest challenges, that being rock modelling. Two broad domains of intrusive type can be seen here. So in the sort of non-textured beige on the left of screen is our coarse-grained monzondiorite, while to the right we can see one of our later phases, our medium crystalline monzondiorite. And in the middle we have our porphyritic intrusive, almost forming a diap here. Now we've got an inferred plunge of that to the north. It's consistent with our interpreted plunge of the porphyritic intrusion, and that's where the money's on. We think that's probably what's related to epithermal mineralisation in the area. So mineralisation can be broadly classified as either structurally controlled or primary or in either primary or secondary structures, or contact controlled, so lith plays an important role as well. From the cross-section on the right, we can see that the secondary lode structures coming off the main one are not intrinsically linked to the upward propagation of the faults, and instead interpreted to represent lateral linkage structures between faults and other lodes. Both major breccia vein sets and intrusive phases, irrespective of their relative ages, all plunge back towards the major arc scale transform fault, which is located over on the left-hand side of that cross-section. A major east dipping thrust fault truncates mineralisation at about 400 metres below surface in the central fields area and juxtaposes two lithological domains. So in the hanging wall we can see our standard fields lithologies, but in the footwall we can see a much greater volume of basaltic diking and very potassic monzonitic to cyanitic diking. So where's the gold? Now, before we get bogged down in detail of this, there are three kind of things to point out here. Firstly, 95% of the gold is located in our silica sulfide stage veins, so everything we can see in sort of the red there. Secondly, the highest grades are with our spotty chalcopyrite, phase 1B up in the top left there, while very little grade is actually carried by any of our phase 1B that is sphalerite dominant. We take the differences between the gold distribution of what is effectively the same paragenetic phase to represent boiling, and that's based both on textural features and increase in tellurium and bismuth. The third most important thing to sort of point out here is that there's a general progression from silica sulfide dominant assemblages through carbonate and onwards to sulfate only. We take this to reveal a staged evolution for fields, which will broadly align with this. So as we can see here, we've got our two main major faults dominating the prospect area. So we've got our major arc transform fault on the left, and Fields fault, which is effectively a conjugate. Both have been exploited by our late stage intrusions. The silica sulfide stage, which carries most of the gold, represents a dominantly magmatic derived fluid rising up, fluid meaning liquid and vapour, rising up through these faults. The carbonate stage then represents the result of a collapsing system, that geotherm moving down, and the ingress of meteoric fluids coming straight back through the same structures. On its way back down, it's diluting a lot of stuff though. The sulfate stage represents effectively the final stage of mineralisation, and in very broad terms represents the deflation of the system and exsolution of sulfate vapours. So our silica sulfide stage, as mentioned previously, carries most of our gold and is interpreted to represent a mostly igneous derived component. Phase 1A that we can see over here, dark colloidal silica. The colour is provided by a whole series of very, very fine pyrite. Gives it a very distinct black colour. There's not much gold in that. There's a little bit of chalco, and the gold is principally as electrum and tellurides from our information up to date so far. Phase 1b, on the other hand, contains the greatest gold value and is readily identifiable through this slightly opaque colloidal silica and this spotty, bubbly chalcopyrite texture on the right. Also phase 1b, we can see there, we've got the typical low iron honey sphalerite with rims of galena, all associated with rhodochrosite. As you can see from this scale bar here, the gold is generally too fine to see with the naked eye and even a pocket microscope, as we've tried very often to try and see it. The spotty chalcopyrite texture is our best visible indicator that we're probably carrying some gold. In the chalcopyrite, gold is free with a relatively high degree of fineness, although there are small amounts of electrons and tellurides also associated with this and phase 1a. Of course, some free panable gold is always good fun to pan out of the AC bags, show the fieldies what gold actually looks like. Stage 2 is dominantly carbonate. We've split that into two different paragenetic sequences, differentiated by the abundance of rhodochrosite and high iron calcites. That's exclusively in phase 2. We can see that running through there. And we can also see in these images here clasts of phase 1b. So that's our gold. That has very low gold. The carbonate stage, as we've said before, is interpreted to represent predominantly meteoric derived fluids, though there is probably some component of magmatic derived fluids as well, particularly in association with the rhodochrosite phase 2. Boiling is still taking place. We've got some really nice lattice textures all the way through and bladed calcites, but it just doesn't really carry that much gold. Interestingly, phase 3 in particular, so down here, we can see cross-cutting primary mineralisation breccia veining. It doesn't necessarily follow the same structures as it does in phase 2. So we estimate that to the closure of the system, the stopping of the epithermal mineralisation, to be coincident with some sort of closure and broader arc-related structural event. The final stage of epithermal mineralisation is dominated by sulfates, so gypsum and barite. Now, there's a bit of barite in phase 2, but overall we really only see this is sulfates, particularly gypsum, that we can see running through here with our last stage, and carries no gold, and basically it's only really useful for delineating our fairly major structures. So alteration styles, how do you know you're getting close? It's extremely narrow. They're fairly standard assemblages for intermediate to low sulphidation epithermal end members, dominated by elytic assemblages. Proximal alteration is characterised by illite, chlorite, prehnite, carbonate assemblages close to mineralisation. That's moved outboard to epidote plus or minus hematite assemblages. Prehnite is particularly strongly associated with our late phase 3 carbonates, we can see cutting through here. And so effectively, really what we're looking at here with these ileic dominant assemblages, temperatures less than 250 degrees, low pressure, high oxygen fugacity, and fairly alkaline pH. Alteration is strongly magnetite destructive and blitzes plagioclase and other high anorthite component igneous plagioclases. The key thing probably to note, it is extremely narrow, and it is extremely hard to, it's extremely easy to call a hole probably a little bit early. So just be aware of that if you ever drill into this stuff. So variations on the theme. So one of our main characteristics for identifying the different phases of intrusions are the presence of this silica albite metasomatism. So that really gives us our paragenetic sequence on intrusions, particularly the early intrusions. We also see, and we're starting to see from recent drilling, with depth, we're seeing the conversion of illite to muscovite. So that's a very clear sort of temperature gradient going above the 250 degree sort of area. And we're also seeing that moving to the north as well with that northerly plunge. So I guess one inference from that might be that our boiling is controlled by vertical ascent. So geochemical pathfinders, how do you find fields like intermediate to low sulphidation epithermal geochemistry? Narrow gold veins. This is key. Very easy to miss in AC. Like the best thing to find gold is gold, but unless you're willing to pattern drill at 25 metre spacing holes, you may miss it very easily. So subsequently, gold grade is not the best. Our best district scale indicators are high manganese, so above 0.5%, and high barium above 0.1%. That really defines, as you can see in our image over here, really makes fields stand out from some of our other prospects, which carry a fair bit more arsenic and copper. There's a bit of copper at fields, but it doesn't stand out in particular. Tellurium is another really good one as well, and that's all associated with our sulfides, as is zinc. So why are we seeing this sort of stuff? It's all about the gang footprint rather than the sulfides and associated gold, as well as dispersion. So we can see here that effectively our barite stays put. It's distal, it's late, and gives a big footprint to the system, whereas our rhodochrosite breaks down to pyrolusite nodules, and so that's why it's effectively staying put, no mobility. How do you know you're getting close? Copper and bismuth. Any sort of copper and bismuth above 500 ppm, bismuth above 1.5, you're getting pretty close. Distal, just to sort of reiterate, high manganese, high barium. Geophysical identification. How do we find it with geophysics? Thankfully, we've got a large number of high-quality data sets. Thank you, Theo. And we can see up here that sort of the more salient messages to take are this big mag low, this very, very strange gravity feature which correlates with EM and IP, and this is a three-dimensional model of our major transform fault and the antithetic folds load. So, mags, probably the best thing to see. Alteration is strongly magnetite destructive. We can see a much broader zone down here of demagnetization, magnetite destruction through here, than is actually defined with our air core gold contours down through here, which is greater than 0.5. It's very large. It's at least 500 by 1200 metres long and extends quite some distance along the arc transform fault. The 1VD, there's some subtle mag low linears, and these tend to correlate quite well with what we know is the orientation of the major auriferous loads. Basically AGC, automatic gain control, is really just useful in identifying sort of the major imbricate thrust sheets that you can see through here. So gravity, prominent half donut shaped anomaly. Why? Most of the gold is developed around the margins, so it is fairly important, and I'll just point out some historical wide-spaced sampling that's identified anomalous gold up to 17 grams over here as well. They all sort of develop on the edge of these gravity contours. GLE, gravity layer extraction, highlights the shallowness of the feature, and it's related to the thickness of regolith and transported cover over the top. So we can see down here from our pattern AC drilling, from depths to basement, matches very, very well. We also see it in the airborne EM from the state survey, and the IP that we've done where it is identified by a chargeability greater than 3 millivolts per volt. It's clearly a topographic feature. The cause and relationship to mineralisation is somewhat unclear. It's very easy to sort of go, oh, well, it's probably a sinter, but it's not. Our AC intercepts do not indicate any significant silicification related to it, but there is some indication that particularly the margins to the south here are preserved partially by increased quartz-bearing veining. Another thing to point out here is that IP is fairly useless. The resistivity of the vein system is swamped by the intrusive resistivity, and the mineralisation is not chargeable enough to see with a reasonable station spacing. That's despite disseminated pyrite being, very, very intimately associated with the breccia vein systems, less than 50 metres away from the edge. So our current thoughts. At present we believe, and it's pretty much just a pattern recognition feature at this stage, but we believe this last stage of intrusion that is probably related to our epithermal mineralisation is responsible for the half donut. In association with this porphyritic late intrusion, the fringes are full of silica albite metasomatism, and so we believe that at some depth under here, possibly not particularly well recognised from air core, that is related to preservation from erosion and subsequently the paleotopographic feature associated with fields. There is clearly some structural control on this as well. One of our thrust sheets runs over through the back here, and another one runs down through here, and the field's load itself is essentially a major structure running along through here, effectively cutting off what may well have been a full donut. Challenges and opportunities. Now, our challenges are not unique for gold explorers working through the Macquarie Arc. Aside from the standard economic considerations regarding narrow high gold load systems, the complex linkage structures and load stacking arrangements, we also have a reduced field season due to the intensive cropping for which the ground is used for most of the year, particularly during La Niñas where the weather gets the best of us. On the geological side, there's no really concrete evidence for what is controlling our boiling zones, though the evidence is that it is vertical ascent and fault valving. Add to this the standard levels of structural complexities of faulting, and in particular understanding the magnitude of throw on the thrust faults, and there's a few things we've got to work out. It's early days, and there's still a long way to go before a critical assessment of the economics can be ascertained, but there is a lot of upside. For one, mineralisation remains open in all directions and now exceeds 650 metres of known strike length. We know that the major arc transform fault also contains epithermal gold mineralisation, and so presents the potential for gold along an extremely long strike length. That's about 3.6 kilometres in strike. There's also a fair amount of areas within the epithermal province that contain analogous geophysical signatures. So just looking at the mag lows through here, there's quite a number, particularly in association with that transform fault, but even further south. So there's quite a bit we can do. In terms of upside, there's an increasing potential of porphyries at depth. We're starting to see, as we move to the north, particularly, and links back into our temperature gradient that we see with our illite changing to muscovite, we're starting to see an increase of quite thick porphyry veins. So we've got moly down here and even magnetite. So we're seeing a sort of a decrease in that oxygen fugacity away from hematite stability towards magnetite stability. So there is a chance, and one of the key recognitions about intermediate sulphidation systems as opposed to the adularia dominant low sulphidation air members is the relation to prospectivity of nearby porphyries. Low sulphidation epithermals can be quite some distance or completely unrelated to porphyry mineralisation, whereas intermediate sulphidation can be quite proximal. Think Wafi Golpu. So in linking to that, we kind of view fields within the broader context of the porphyry epithermal province in which we are, and that sort of gives us a better indication about our further prospectivity. Having plenty of room always helps, and of course the similarities between this mineralisation that we've just described at fields and those of our arc neighbours at Cal gives us pause to consider just how much mineralisation might be hiding just below the surface. So, thanks. Oh, and I have to